And so we're happy to have Kenji Fukaya from Simons Center for Geometry and Physics, and he will speak about homological mirror symmetry over Novikov rings. Kenji, please.
Yeah, thank you for introductions. I'm very happy to talk here. And my title is a note on homological mirror symmetry over Novikov ring. So I want to emphasize this is over Novikov ring. Nowadays, there are many works on homological mirror symmetry, but as far as I know, most of them is either over ground field or Novikov field. So I just want to remind you what is Novikov ring and what is Novikov field. So we consider over this. What was it? Yeah. So we work over this ground ring. That is either Q real number, complex number, or maybe integer sometime. And we consider this lambda 0. That is this kind of formal series. This coefficient is on this ground ring, and this exponent is a non-negative real number, which converges to plus infinity. And if you invert this formal parameter t, then you got this Novikov field. So here, this exponent is allowed to be negative number. So this is a field and this is a ring. And it is kind of known to several people working on symplectic geometry, is that if you consider this Lagrangian Floer theory over Novikov ring, it contains something much more information than the Lagrangian Floer theory over Novikov field. Especially if you consider something like Hamilton dynamics or kind of more on this symplectic world, then this working on Novikov ring has some advantage. So I want to discuss what we can say, how this homological mirror symmetry is related to this working on Novikov ring. So I want to introduce some notations and some notions I want to use. So let me consider compact symplectic manifold. And we take a finite set of Lagrangian submanifolds. We have this Lagrangian submanifold of M. This is a half dimension of M, and the symplectic form vanishes on L. And then there is some MPT category, which I want to say filtered MPT category. So its object is a pair of Lagrangian submanifold of this element and B. That is called a bounding cochain. So bounding cochain is somehow, in general, Lagrangian Floer theory, you have this just usual Floer homology. Then this D square is in general non-zero in this generality. But we can use certain element of odd dimensional homology, which satisfies something called a Molar-Cartan equation. And if you deform your Floer's boundary operator using this bounding cochain, you get this is actually becomes zero. And you have this Floer theory. So that's a story I developed with Ono. So that's called the bounding cochain. And so we have this MPT category whose object is this Lagrangian submanifold plus bounding cochain. And you have a morphism. So morphism is a kind of,
Kenji, do you assume that they are somehow transversal? Or
yes,
not?
yes. All two different Lagrangian submanifolds are assumed to be transversal. Yes, okay. Or at least clean. So you have this L prime. Then this is just a sum of this intersection point. But in some cases, especially if L is equal to L prime, then it's not transversal, but it's still clean. So in these cases, this is something like you can either take homology group or maybe take this it's drum complex or anything like that. Okay, so this is an MPT category.
Could you please say something about how the dB is related
dB
with the differential?
Okay, yeah. So you have this two Lagrangian submanifold. Yeah. You have this two Lagrangian submanifold, L and L prime. Then the boundary, so you have a PQ. Q is just a number of such a disk. So that is usual Floer's definition. But then we want to kind of, we have this kind of B here. So we count this disk so that it intersects with this chains. So dimension is different. So this is something called EB prime. So this is exponential. So you have arbitrary many B and arbitrary many B prime, which we put here. And that is this deformed boundary operator.
Okay.
And the condition that this is a 0 is somehow follow from the smaller Cartan. I mean, so this is in a simple case. This is something like x go to dx plus x wedge b and b prime wedge x. So this is something like a flat connection. I mean, the connection is I mean, drum differential is deformed to a flat connections, deformed to a kind of local coefficient. And in that case, this is something like equation db plus b wedge b is 0. So this is the usual standard molar Cartans. And you have this A infinity version. And what's different is that in this case, you start from d squared is 0. So kind of origin is contained in a molar Cartan. But our molar Cartan equation is inhomogeneous. It means that 0 may not be a solution, but still you have a solution, you can just use it.
Okay, thank you.
Yeah. So now I want to explain something about the Yoneda embedding. So you have this AVT category. So it's a kind of category. So you have object, and you have some object. They have this space of morphisms, and you have this infinity operations. Goes to C0, Ck. And it has satisfied some kind of infinity relation. So this is some kind of homotopy version of category. And so the one important thing I want to use is this Yoneda embedding theorems. So in a version of Yoneda embedding theory of this infinity category is the following thing. So I want to define the notion of module over infinity category. It's the following thing. So suppose you have an object of the category, then it associates some chain complex. And suppose that you have a k plus 1 object, then you have this BC0, which has, and then you take this morphism space, and you have this kind of thing. So, I mean, in the easiest case is that you have just a ring. So ring just has a 1. So you have this, so you have ring A, and you have a module. This means that you have this B tensor A go to B. So this is a module. And the APT category is some kind of a generalization of this ring. And you have a notion of APT module, light module. And the set of APT light module is called, it becomes some called a DG category. So DG category is a category so that the morphism space is a chain complex and the composition is associative. So this is a special case of APT category. And Yoneda embedding is that if you have any APT category, then you consider this a DG category of light modules, and there is an embedding. That is Yoneda embedding. And that is very natural generalization of usual Yoneda embedding in a case of category theory. So you have an object here, this object. Then you want to define this light module, how to do it. So you have another object, C prime. Then you consider this morphism space. And that is some kind of chain complex. And then this is a kind of light module. And this operation of this light action is exactly something like the composition operator. I mean, this is some kind of generalization. So you have a, so if A is a ring, then A itself is a light A module.
Mm-hmm.
This is a very simple, well-known construction in algebra. And this construction of this Yoneda embedding in infinity category is just a kind of category version of these constructions. And Yoneda lemma says that this is a kind of fully faithful embedding of the category. Okay. So now using these notions, I want to define some next notions. So we consider a set of Lagrangian submanifold of M. And I want to say that this set is a weak generator of this NVT category. It's the following things. So if you take any finite set of Lagrangian submanifold of M, then we consider this category. So this is the NVT category whose object is an element of L, and Floer homology is a morphism. So we can naturally embed, just put extra L0, and then we take this Yoneda embedding, but other kind, we only consider this L0. So this gives the light L cap L0 module, but of course L0 is subset. So we have this light L0 module. So this is I want to call Yoneda L0. So you have any L, then you have this Yoneda embedding to the category of light L0 module. Basically, this means that you have any L, and then you can just consider this Floer homology of L and L0, where L0 lands on element of L0. So to understand L, we just take this element of L0 of this given set, and we consider this Floer homology between L and L0 only. And if this embedding is kind of enough faithful, then this L0 is called a generator. So I mean, you just consider usual abelian categories. If you have an abelian category and you have some object, and you have similar functors, and if this functor is a faithful functor, we can regard that this set is a generator. So this is a kind of analog of that notion in NVT category. But I just want to use some notion of Gromov-Hausdorff distance, which I will explain later. And in place of assuming this is a fully faithful embedding, I want to say that this guy and its image is very close to isomorphism. It means that some Gromov-Hausdorff distance between them is 0. So this is what I mean by weak generator. So this is a notion of a weak generator. And if you know something about homological mirror symmetry, many proofs of homological mirror symmetry is based on finding a good generator of the category. I mean, homological mirror symmetry relates this Lagrangian thing to some derived category of coherence sheaves, but the category is something very hard to calculate. So you are supposed to calculate the Floer homology for all Lagrangian submanifold, which is almost impossible. But in certain cases, you have a good set of generator, so that you only need to study those a small number of Lagrangian submanifold, and that is a kind of very key idea to prove many homological mirror symmetry in many cases. So I want to try to do it over this Novikov ring. So I say the following things. One can do, there are similar notion for this over Novikov field. And in the case of Novikov field, we can just say that the Gromov-Hausdorff distance, in place of Gromov-Hausdorff distance, that this is a full subcategory, homotopy equivalence to full subcategory. It means that you have this L, then it goes to this light module. And you assume that this is homotopy equivalence to the image. So this is the case of lambda, and this is some version of the notion of generators. And so this is something I want to do. So we want to find some good generators. And so I want to immediately remark, in a case over this Novikov field, in many cases, there is a good finite generator. For example, for compact symplectic manifold, I think this notion by conceivage of smoothness of category or something is related to this, you have a good generator consisting of finitely many solution elements. However, as you will see this thing that it seems almost impossible to find a generator consisting of finitely many Lagrangian submanifold if you work over a Novikov ring. In a sense, NVT category over Novikov ring contains so much information, there's too many informations, so that you cannot capture all the information from finitely many Lagrangian submanifold. So this guy is supposed to be a kind of infinite set. But anyway, so now I want to show, so the main problem is can one find a good generator over a Novikov ring? So good generator over Novikov field is discovered by several people and used in various purposes. But so what happens if you just consider ring in place of field? So the first example that this kind of thing is let me consider a very easy case when M is a two-sphere. You have this equator. And you can just take this L0 as just a single equator as a Lagrangian submanifold. And it is very well known that this one is actually a generator over Novikov field. But as you see that this is not over Novikov ring. So what is homological mirror symmetry for S2? So for S2, the mirror to S2 is known to be a Landau-Ginzburg model of this particular function. So T is a formal parameter. So you have this y1 plus y2 plus T divided by y1, y2. And this is Landau-Ginzburg potentials. And the critical point of this function is a 2 point. I'm sorry, this is not one, this is T half. So you have these 2 points plus 1 plus T half and minus T half. And these two actually correspond to this equator with two flat connections. So this is S1 equator with trivial flat connections, or minus 1 flat connections, and they correspond to these two generators. So these two are actually generators. So what it means? So what it means? So you have any Lagrangian submanifold of S2. There aren't many, but there are actually many. But if you know the Floer homology of L with this equator, with these two bounding cochains, then this knows all of everything for this Floer homology of Floer theory of L over lambda. So this information is strong enough to determine all this Floer theoretical information over your Lagrangian submanifold, but over Novikov field. And I want to claim that if you start Novikov ring, then this claim is wrong. So let me consider this S2. And you have two Lagrangian S1. So this L and L prime. And I assume that you have this kind of L. Then S2 minus L is a kind of two domain. And I want to assume this volume is equal. Otherwise, Floer theory is trivial. So I mean obstructive. So now what I want to say is that we consider this L and take Floer homology with the equator. This is just a rank 2. You have two intersections, and this lambda 0 plus lambda 0. And we take this L prime and take Floer homology with S1 equator. And this is also lambda 0 and lambda 0. And this is a module structure. This is also a kind of homology. This is a easy thing. So this is a homology of S1 over a ring. And this action is also very easy. So this module together with this action is everything about this module category. They're the same. So this L and L prime, you cannot distinguish L and L prime using these two modules. So it means that you consider this f of this L prime. I'm sorry, this infinity category consisting of these two objects. They have this module category over this equator. And this is not injective over lambda 0. Two objects, which is different here, is completely different here, becomes the same. So this is not embedding. So this is an evidence that I mean, if you work over lambda 0, just taking equator is not good enough to to obtain generators. So how
on the mirror dual side, how it can be seen?
So on the mirror side, the problem which is not so much well understood. Just something like related to the problem. What is the Landau-Ginzburg model over Novikov ring? And that's a delicate issue. And if you know this generator things, maybe I can explain more. So the conjecture, well, I think it's almost a theorem, but I didn't write it up, so I write it conjecture the following things. So let me consider the case of S2, and we consider L0, the set of simple closed geodesics containing north pole. So you have this is S2, and you have this north pole and this south pole. And you consider this round sphere, S1, equator, but you consider all this family you have this S1 many this equator which contain this North Pole. So you have this set of S1. And we consider this all this S1 as a generator. Then the statement is that this set, which is infinite but kind of not so bad, you have just S1 many, and this is a generator even over lambda 0. And so, but the S2 case is a bit too easy. So I want to go a bit more. It just this n power of this S2. Then we consider this product of this. So you have this. This is just a product, but you have this T1, Tk, Tn. So Ti is just this family. You have this S1 many family. So you take this. So you have this Tn parameterized family of Lagrangian Tn, and the claim is that this family is a generator of this category over lambda 0. Maybe after I claim this, I just mention a bit about what this Jan asked. So let me consider this. So let me consider the spectral of lambda 0. This is something like a special point. It's just a ground ring. And have another point correspond. So this is a generic point. This is a special fiber. And you have this guy is kind of to interpolate them. Then if you consider some kind of algebraic geometry or some family over this at the generic point, you have just 2 points. It's just a critical point. Right? You have just 2 points. But then on a generic point, this guy kind of, you have a S1 parameterized family of objects. And these two objects are kind of different objects over this lambda 0. But all these S1 family of objects became just degenerate and just became the same object. So you have some kind of non-compact space over this scheme. So that it's fiber generic point, fiber is just 1 point. But if you go to this more general point, you have a much bigger category.
Yeah, but so algebra geometrically, it looks as a choice of a model because you have your non-Archimedean field, which is lambda, and lambda 0 is a ring of integers.
Yes.
And so, of course, after localization, you can get some isomorphic objects which are different over the spectrum of the
So I believe you have this infinity category whose object set is just S1. Oh, this is over lambda 0, and then we know that the mirror of this Lagrangian Floer theory over S2 is just the kind of category module over this category. So that I think is a kind of homological mirror symmetry in this case of S2 over lambda 0. And we can extend it at least over S2, S2 to the power n. So that I think is a kind of way how we try to study all this homological mirror symmetry over lambda 0. Okay. So now I want to show you a bit why this S1 parameterized family is strong enough to detect. So this is L1 L prime. So this is a picture in S2. And you have this L and L prime. And so this is a North Pole and this is South Pole. And we have this S1T and S1T prime. And then I want to say that this L and L prime gives a different module over this. So that's following things. So we take this X and Y. And this X, Y, this X and Y is an element of Floer homology of which one? L prime, right? L prime and S1T or S1T prime. Then we take this product, and if you know this product, it just kind of comes from the counting of this triangle. And so you get this one, North Pole, but you have this weight is on a simplex area. So you have this T to the power A of NP, North Pole. So this is the product structure. So this is for L, and this is for L. So then you do it for L prime. You have these 2 points. Then you can calculate the product, and it gives also North Pole, but the area is different. So this is a T A plus B. And this A and A plus B is different. And over Novikov field, T is invertible. So this difference is just a kind of become just change of the generator. But over Novikov ring, this is very different. So over Novikov ring, this Yoneda factor associated to L is different from the Yoneda factor associated to L prime. So if you consider all these module structures of this S1 parameterized family, you can distinguish these two objects. And in a slightly different situation, so you have this S1, this is North Pole, this is South Pole. In this case, you can consider this L and L prime in this picture. So in this case, you don't use a multiplicative structure. In place, you use a torsion. So you consider this Floer homology. Then you see that there are many intersection points, and the boundary point is something like this. So this guy has a lambda zero torsion. Lambda zero torsion means that so this Floer homology is something like there are two free factor and something like e to the power ai lambda zero. So this is called a torsion. And these torsions has enough information to distinguish the L and L prime. And of course, you know, if you go from lambda zero to lambda, just this all torsions are destroyed. So you cannot distinguish it. But this torsion knows about the difference. So there are two somehow slightly different mechanisms so that the two different Lagrangian sum manifolds are detected by this S1 parameterized family. But this is the case of S2. And probably in S2 to the power n case, it's rather hard to see what happens. But the statement says that the theorem says that this is also possible in higher dimensions. And I want to mention the following thing. So suppose you have two objects, two Lagrangian sum manifolds together with bounding cochain. And suppose that these two are kind of equivalent objects over Novikov ring. Then the claim is then actually the Lagrangian sum manifold L and L prime is equal, that's theoretically. So this Lagrangian Floer theory over lambda zero is very powerful. So so that if these two objects are the same, then the Lagrangian is actually the same. So it contains kind of very rich information about the Lagrangian sum manifold itself, or maybe Hamiltonian dynamics. This is never true over lambda, because Floer homology over lambda is actually invariant of Hamiltonian diffeomorphism. So you cannot say so much. But so this implies that you know, so this note implies that if L0 is a generator, if you know Floer theory over L and L0, or L0 moves as a module, then you know what is L actually. So this is kind of rather big information. So I want to so this is yet a conjecture, but I think I can sketch the proof. I hope I can prove it in the near future. So this is related to generating criterions by Abzai and several people. So what is Abzai's generating criterion? So you consider this L0 a set of Lagrangian sum manifold. Then we, as I mentioned, we have this empty category, and whose object is a pair of Lagrangian sum manifold and its bounding cochain. And then there is a map called the open closed map, which goes from Hochschild homology of the which goes from Hochschild homology of this empty category. This is Hochschild homology to the symplectic homology in case M is non-compact, or just usual homology in case M is compact. This is called the open closed map. And it is something I cannot explain in detail, but it counts something like this. This output, this is L, and you put some point here. This is basically what is called the open closed map. And this generating criterion relates this open closed map to this generator. The theorem says if the image of this open closed map contains identity, so identity is either in this group, then this L0 is the so-called a split generator. A split generator actually means weak generator. So it means that this image of this open closed map contains the identity or unit, then it is a generator. And Abzai proved it in a non-compact and exact case. And in a paper he published in a publication IHES. And in the case he worked over grounding, maybe Z, I think. In an exact case, one can safely work over Z. But we consider compact case, and it is supposed to be written with Abzai and Otaono, but to my shame, it is still, I am still on the way of writing. But in this case, it is correct, but it is over Novikov field, not Novikov ring. And actually, when I looked at the proof, not yet written a bit, I think it works, the proof works over Novikov ring. However, it seems likely that the assumption is never satisfied over Novikov ring. So to prove it over lambda 0 is mostly empty. So let me say one example. If you consider this S1 equator contained in S2, and you just consider just the equator, and then image of P star with this open close map contain T half of identity. So let's say that P just count this kind of thing. So you have this S1. You have this upper half plane. So you put some. So input is something like maybe point class in a homology of S1. Then you take output. So it just covers everything. And the symplectic area is half. So this is the weight. So image of P star is T half of 1, and over lambda, T half is actually invertible. So the image contains 1, but over lambda 0, T half is not invertible, so it doesn't contain unit. And as you will see that it's hard to obtain this one itself. So, but then there are some related conjecture. Suppose L0 is a finite set of Lagrangian submanifold of your symplectic manifold M, and we consider this open close map from Hochschild homology to homology of M, and we study over lambda 0. And suppose that this image contains T to the power delta of 1. That's a similar situation like as in these previous things. Then the conclusion is that so we consider this Yoneda functor. So for any L, we consider this Yoneda functor. So this MVD category associated to L to this category of light L0 module. So we want to compare this original thing and its image by Yoneda functor. And the claim is that that's some I will define later. Gromov-Hausdorff distance between these two categories is smaller than probably delta itself, but some universal constant times delta. It means that this is something like enough dense. So it's something like approximate the original category. So this module category, image Yoneda functor is close to the original one. And I think Bilan Cornea study a similar kind of things. But in his case, in their case, I think he used genetic criterion by Paul Seidel, genetic criterion, which Paul Seidel used to study this Kardec case, not this upside one. But I think the idea looks somewhat similar. And they don't use this particular notion of Gromov-Hausdorff, but the work looks related. But anyway, so this is the kind of conjectures. So I want to use this. So I want to explain how this claim, this conjecture implies that first claim of this criteria for this S2 and S2 to the power n.
So about this Gromov-Hausdorff, should we just know that if the distance between something and Yoneda image is 0, then they are equivalent, or what?
Unfortunately, it is not equivalent, but so let me mention the following things. So suppose you have this C1, C2, to MVT category, and the Gromov-Hausdorff distance is 0. What do you mean? So we have some object.
Which you have not defined this.
Yeah. I will define later. So it takes some.
Yeah, okay.
The set of object is somehow isomorphic. This is isometric. I will explain what is the metric, but together with this metric, they are isomorphic. And you have two things. C prime, C1 prime, and this C2 and the C2 prime. Then we take this Floer homology. I don't say they are isomorphic, but you have this for any positive epsilon. You have this phi epsilon and psi epsilon. And you compose phi epsilon and psi epsilon This is t to the power epsilon. And you go do this in opposite way. This is also t to the power epsilon. This is something called almost isomorphic. And all this phi epsilon is compatible with multiplicative structure. So these two, if this is isomorphism, it implies that this is the equivalent, but it's almost equivalent. Okay. So now I want to consider the case. Oh, let me see. Yeah.
So the idea is that the T epsilon is a factor which is acting on the categories of the.
Yeah. T epsilon is just a multiplication number. So it's T0 is just one. So it's identity.
The C1, C2 are categories. So then you should I understand?
No. This is C1, C2 is the object.
Okay.
And this one is the Floer homology. So it's a lambda zero module.
Okay. Yeah. Thank you.
So I want to explain how this kind of thing works for S2. So we consider this n.
So above you showed the Gromov-Hausdorff distance is less than C delta, right? If
Yes.
the valuation of the image of some element in Hoxton homology is delta. But how does it show? It's actually zero. I thought theorem was saying it's zero.
No. So I'll go to data, but I mean we go to the limit when delta goes to zero.
Okay.
But I'll explain soon. So we consider the case of S2.
So you will keep enlarging L and it will become infinite?
Yeah. Increasing n. So we have considered this n closed geodesics containing North Pole. So that you have Li and Li prime. So this you have this domain. So this is something like this. And this domain. Suppose that this area is 1 over n. So you have this n, you have kind of dense set of some n dense, 1 over n dense set of this S1s. And then this n pole regarded as this intersection to xi, and yi, this intersection is yi. So we take the sum over xi tensor yi, and one can see that this is the Hochschild cycle, and its image by open closed map is 1 times t to the power 1 over n. So this means that this everything is not yet a generator, but is kind of a 1 over n close to the generator. And if you take all this S1, that means n go to infinity, then you obtain this generator. So I want to mention a bit more non-trivial case of S2 cross S2. So something I want to show is that you take this Mn plus Mn. You have this n S1 in the first factor and n S1 the second factor, and you take all the sum. And then I want to show that this P star from this Hochschild of F Ln times Ln, the homology of S2 cross S2 contain T to the power maybe C to the power n of identity. So how do we do it? If you look at this definition of P star, it means the following thing. Suppose you have 2 points on S2 cross S2. So I want to find some U from disk to S2 cross S2. So that its boundary lies on this Lagrangians, and 0 goes to this particular point PQ. And the area of this homological curve is something like 1 over n. And you can find this, then if you look at this definition of open closed map, you find that this is a kind of almost a generator. So how do you find such a U? The situation is the following things. So P, so let me take P and Q. So P and Q are point in S2. Then P lies here. So in something like between Ly and Li prime. And Q is here. It's Lj and Lj plus 1. Then we take this map U1 from this to this domain. So that 1 goes to this X and 0 goes to P. And Y, there are some A which goes to Y. And you have U2 from disk to this domain. So that 1 goes to X and 0 goes to this Q. And Y is an inverse image with a P. Now I take this U so that it's U1 and U2. So it's a map from disk to S2 cross S2. Then what is this? So you have the 3.1. One goes to this XX. And A goes to Y and something. And B goes to and something and Y. So you have the 3 lines. And the 3 lines goes to this. So this line, so you have the 3 lines, and this disk, the boundary goes to this union of these 3 things, and the 3 kind of marked points goes to XX and YLJ and LIY. So we take this element XX, Y identities. Identity is the kind of intersection of LY and LJ and LJ, and identity of YJ. These guys are again Hoshi's cycle, and it goes to the fundamental class. And we take some. And its area is something like a t to the power 1 over n2. So this means that in S2 classes, you can do the similar business to show that this is almost a generator. And if you see that you have n power, you can do the similar constructions to have n gons, and so that the Hoshi can go to this generator. So it means that this map, Yoneda embedding, and so its image is smaller than c to the power n. And then I want to go into infinity, and you get a theorem, which is not yet proved theorem, but something like we can prove this kind of ways. And we need this limit process, so we need some kind of topology. Okay, so now this is somehow how we can prove it. And then this is the case of
Kenji, can I ask a question? So
Sure.
if you know now these generators, can you build the mirror just by doing this family Floer homology, and you get?
I mean, so what I mean by mirror is a bit kind of delicate because it's not a complex manifold, not random gizmo, but in the usual sense. But in this case, you have, for example, you have this family of family S1 parameterized family of so you have some infinity category whose object set is S1, and its morphism set is not so very complicated. You can calculate.
Yeah.
And S1 to the power n case also can be, it's just a QNS. So it's not so completely difficult to define. But then what we know is that the mirror is this infinity category of all Lagrangian submanifold. It's just a subcategory of a module category. And so this module category looks something similar to, looks something like a Landau-Ginzburg model over lambda 0.
Yeah.
So that I believe to be some kind of a homological mirror symmetry statement.
Okay. But do you expect to get really mirror or this kind of almost?
I mean, what do you mean by real mirror is difficult. So what is, that's, I mean, it's not Calabi-Yau case. So what is the Landau-Ginzburg model of lambda 0 is a bit.
No, I mean, like you can speculate, like family of the formal over the spectrum of lambda 0 of varieties with a potential which is kind of not a function but an element.
Something like this, yes.
Yeah, I mean, it's non-Archimedean potentials. People consider them, but rather over field. Maybe.
Yeah, I mean, over lambda 0, it's, I mean, I think this in also in algebraic geometry side, this kind of formal deformation theories and the category of Poiret over there kind of thing is interesting thing to study, but I don't know how much it is studied.
Well, somehow it's been studied, but again, it's rather not algebraic geometry, it's maybe analytic geometry because
Yeah. And also it's something related to some kind of similarity with arithmetic algebraic geometry of mixed characteristic. So
yeah, but it's basically for the same reason because
yeah.
Okay.
So this is a case of S2 cross N, and probably in a case of projective space. So we consider this Kähler isometry of projective spaces. And if you take one clipboard tori and you move it by this group of isometry, you have a finite dimensional family of kind of clipboard like torus. And I believe that this is a weak generator, but I don't know how to prove it. And something more ambitious. But projective space has a lot of automorphism, and if you go beyond it, it's kind of hard. Something I can expect for you have any compact symplectic manifold, and you cover by finitely many Dalbu chart. And because of this kind of thing, it's a kind of clipboard tori contained in Dalbu chart, or the clipboard tori. This is still finite dimensional family. And the conjecture is that this L0 is the generator. But this is harder to prove, and I don't know I cannot prove it. But the argument I just explained is somewhat related to this kind of things, but I don't know how to prove it. Okay, but since I have 15 minutes, I want to, an important thing I want to explain what is the Gromov-Hausdorff distance. And I first review the Gromov-Hausdorff distance in a classical metric space context. So suppose you have two compact metric spaces, and the Gromov-Hausdorff distance is smaller than epsilon, if and only if there is another compact metric space Z, so that these two metric spaces are isometrically embedded. And the Hausdorff distance between this Z is smaller than epsilon. It means that you have any point P on X1, then there's a point Q on X2, and so that its distance is smaller than epsilon, and vice versa. So this is the Gromov, the classical definition of Gromov-Hausdorff distance of between metric spaces. And something I want to do is just to modify these definitions so that the compact metric spaces are replaced by infinity category. So first of all, I want to suppose you have this filtered infinity category, the infinity category of a Novikov ring, and we consider the set of objects. And something I need to explain is that this set of objects has a pseudo metric. That's called, that I want to call Hofer metric because it is related to Hofer geometry.
Sorry, because now you started to give definitions, so I'll be a bit more pedantic. So OP-C is set of objects, so it's a set of classes of isomorphisms or whatever. Because Gromov-Hausdorff distance, it's not a distance on metric spaces, it's on isometric class, it's a metric on
Yeah,
isometric.
so this is a kind, so it is pseudo metric actually. You know, Gromov-Hausdorff distance 0 is almost isomorphism, but it's not isomorphism. That's a bit unfortunate, but
because your object has some symmetries, kind of.
yeah. But this is a APT category, and it is just honest category. So it's just that, and also it's a small cat. I assume it's small category.
Okay.
So object C is just a set, and it is actually it is a pseudo metric. It means that the metric 0 does distance 0 does not mean it's isomorphic.
Right.
So this Hofer distance is extremely smaller than epsilon means the following thing. You have this two objects, C and C prime. And you have morphism T from this to here. And you have another morphism, the opposite. And you have a kind of self-morphism. So that if you compose T and T prime, it is almost identity. So T epsilon times identity. And it is kind of, you know, this is M1 is a boundary operator. So it is chain homotopic to this T times epsilon to identity. So this is the definition of this Hofer distance. So I mean, if this epsilon is 0, this means that T and T prime are equivalent, homotopy equivalent. But it is kind of equivalent, but up to this epsilon. And this is related to some simple geometric notions. And there are, I just want to mention there is some infinite version of this metric which I introduced. And the reason is something related to unitarity, but I don't have enough time to explain it. But the idea is that you look this formula. This formula looks very similar to Moller-Cartan equation, right? M1s plus M2tt is unit. And if you just expand this honest Moller-Cartan equation, that is this Hofer infinite distance. But probably the time is a bit tight, so I don't want to explain it. So you have two filter infinity category. Then the Gromov-Hausdorff distance between them is smaller than epsilon. It's a form of things. Suppose you have this another filter infinity category. So that the C1 and C2, there are infinity functor from C1 and C2, which is homotopy equivalent to the image. So there are some full homotopy theory of infinity category. So C1 and C2 is a kind of homotopy equivalent to a subcategory. And then for any object of C1, there's an object of C2, so that it's a Hofer distance on this big category is smaller than epsilon, and vice versa. So you see that this definition is very similar to this usual Gromov-Hausdorff distance, but the difference is that this embedding, so object Ci is embedded to object C, but this embedding is somehow induced by some infinity functor, which is a homotopy equivalence. So that is the definition of the Gromov-Hausdorff distance between infinity category. And the theorem is that this Gromov-Hausdorff distance satisfies triangle inequality. This is not completely trivial, but not extremely hard to prove, but it's not completely trivial.
May I ask you, so it's also symmetric, yeah?
Yeah, symmetric is rather easy, yes.
Yeah, so then the only axiom.
Triangle inequality is non-trivial.
Yeah, but then if you said that if the distance is equal to 0, then these two objects are only or almost equivalent.
Almost isomorphic, yes. So it's a kind of metric on almost equivalence class of infinity category.
Yeah.
But
sorry, can you isolate the object from the second, like when you, for instance, when you are given a C1, when you are trying to pick up a C2, can you just take it from the triangulate envelope so that this would be a Morita invariant concept? Would be a derived invariant concept.
I think you want to do it probably you have to enhance it, right? So you can either use this Morita thing by using this kind of Yoneda embedding to enhance this category. So this is just usual infinity category. So the only object set is not enhanced. But of course you can say that if you have any infinity category, you can just make it bigger.
Yes, so you just define TV pies to be, like you just define the distance of TV pies to be the distance of infinity categories to obtain a Morita invariant concept.
No, this is just a distance. So it's this is not a Morita invariant.
Okay.
Morita equivalent categories are probably not Gromov-Hausdorff 0. Yeah, I don't know. Yeah. But you can kind of modify some definitions like this using Yoneda embedding or something too. Okay, so now, but there are one more thing I need to explain. There are something called the gapped conditions. And this is somewhat important. So gapped condition means the following thing. So we have these operations of infinity category. And it is something like a formal sum. So that each of these coefficients is just defined over ground ring. And you have this t to the power lambda I. And lambda I is a non-negative integer. And this gapped means that this lambda I is contained in some discrete set of non-negative integer, non-negative real number. And in the case you can start from finite set of Lagrangian sum manifold, then this infinity category is actually gapped. This is somewhat important. This is basically the consequence of Gromov compactness. And I mentioned this because we proved several theorems about homotopy theory of infinity category, filtered infinity category over lambda 0. But almost all theorems, non-trivial theorems, proved only in the case of gapped infinity category, because the proof uses induction on this exponent. And so if this is not gapped, it is very bad thing like very bad non-data kind of properties. However, as I explained that for this generating things, we need to consider the case when this lambda 0 is infinite. So I want to emphasize, generalize this Gromov-Hausdorff distance to the case when your infinity category is not gapped. And the definition is basically the following. You have two filtered complex over lambda. And you have this injective filter preserving chain map. And I want to say that this is almost a chain homotopy equivalent. It's the following thing. You consider this any finite dimensional sum complex of the target. They have any positives. Then it has something like a homotopy inverse of phi modulo except epsilon. So you consider this one. This is something like a homotopy inverse. And you have this G epsilon. So this means that you have this kind of phi inverse. So that this one is kind of T epsilon up to chain homotopy equivalence. Up to chain homotopy. And this G epsilon is chain homotopy. But you need to like finite dimensional sum complex. So these are a bit cumbersome definitions, but you have some almost chain homotopy equivalent, that kind of notions. And using these notions, we can say that you have a DG category over lambda 0, then there are kind of almost homotopy equivalence of DG category. And this Gromov-Hausdorff distance, without assuming gap condition is the following things. Suppose you have this 2 DG category, and the Gromov-Hausdorff distance is smaller than epsilon, even only if you have a third infinity category. So that this embedding, you have this embedding of DG category, which is almost homotopy equivalent. It means that you have this map. And this map is almost homotopy equivalent, chain homotopy equivalent, not homotopy equivalent. And then you have the similar conditions that object has a Hausdorff distance small. And this is a notion of Gromov-Hausdorff distance. And this one works over in a case when your infinity category is not gapped. So you can enhance it to the case you have infinitely many Lagrangians. So I can just state 2 theorems. One is that this enhanced version is still satisfy triangle inequality. That's a bit more non-trivial because of this almost things, but still holds. And also, you have a Cauchy sequence of this infinity category, filtered infinity category, with respect to this distance, but then it converges. So the set of all infinity category is actually complete with respect to this notion of Gromov-Hausdorff distance. So that's the theorems, and so we can use this to, so for example, if you want to construct this f of L0, in case this guy is infinite.
Sorry, for this second theorem, you don't need the fact that your distance or whatever defines a sort of a Hausdorff topology, because it doesn't. And how can you be sure that the limit
So the limit is well defined. So you can just say that C is equivalent to C prime, if and only if this Gromov-Hausdorff is 0. So this set of equivalent classes, the limit is well defined.
Yeah, but how can you be sure that it's a infinity and not something bigger? You know, like for ordinary Gromov-Hausdorff, you start with manifolds, and in the limit you can get something which is not a manifold. So,
yeah, but yeah, I mean, the limit is something like a complete DG category. And the big difference is that the limit is not usually gapped, but we can prove that the limit is the infinity category, DG category.
And actually, since kind of again by analogy, when you, but maybe you'll finish and I ask you in the discussion, because yeah, like if you take the Gromov-Hausdorff limit of Calabi-Yau manifold, so it's not just an arbitrary, even if it's a manifold, which is not always the case, it's
I think
Ricci curvature non-negative. I mean, there are some conditions.
You know, this topology is a bit finer than that kind of topology. So, so you know that the metric I used on the set of objects is this forward distance. And if you have a 2 Lagrangian submanifold, the forward distance is finite only in case they are Hamiltonian equivalent.
Yeah, but here you have some.
So if you have a sequence of Calabi-Yau manifold,
yeah,
I don't claim that the associated infinity category is a Cauchy sequence. I don't think it's true, probably.
Yeah, but I can consider. Okay, yeah. So it's already a discussion. Maybe you.
Yeah, no. This is almost.
No. I mean, the reason for my question. You know that kind of 20 years ago we proved your conjecture with Maxim. We proved your conjecture with O, that about this. So anyway, I would like to have not as a kind of conjecture and formal statement, but as a theorem, the following fact: you take it's not a Fana case, it's not Landau-Ginzburg, it's rather SYZ. Yeah, you have this Calabi-Yau, n-dimensional in the large complex structure limit, and so we conjecture that it converges in Gromov-Hausdorff sense to certain manifold with
Yes.
with this affine structure and blah blah blah. All right, so this is still open, it's not proven. But if you take the Fukaya category of your degenerating family of Calabi-Yaus, so then we don't know what they are, but we associate it with the limit, with this affine manifold, with this manifold limiting with affine structure, somewhere singular. We associated some category, infinity category, which actually was constructed by you. It's essentially a category of Morse functions.
Yeah.
On this limiting story. So then the question is whether indeed in this Gromov-Hausdorff sense, this collapsing family of Fukaya categories converges to this, again, Fukaya Morse category on the base, of this torus vibration. Can it be proven, or?
So, if you have this SYZ type pictures, you have some M go to this base space, right? And what one can say the following things. So basically, you have M. You can associate this infinity category, right? We given this finitely many four. And this is over lambda 0, right? And the category, so the kind of limit you study that kind of, this they have T, right? And when T goes to 0 or infinity or something, then this one converges to something like,
something, at the level of this A infinity products. Yes, indeed, that's what we.
So the situation is slightly different. That we keep this formal things. So you have this fiber. So you have this kind of ground ring, and you have this genetic points, and you have this single infinity category defined over lambda 0. The limit we are not, I'm studying is not the limit when the T changes, but you have some kind of several of this kind of things and how this infinity category over lambda 0 converges. So the problem could be related, but it's not so much directly related.
I understand. So you do not have just one category over the formal disk, but you have kind of infinitely many, and you look for them. But at least, I understand that it's a different problem, but you have a notion of distance on some infinity categories.
So I have to say that in the Calabi-Yau case, probably this you need to modify this kind of distance, because if it was just T2, then you have this kind of S1s, right, parameterized by this fibers. Then this Hofer distance S1T and S1T prime is actually infinite. They are not Hamiltonian equivalent. So the object set is kind of, so the Hofer topology for this object set probably is not correct topology. In a case of this family of this S1 on S2, this family of Floer homology is a kind of family of S1s which are Hamiltonian equivalent to each other. So the topology we use is this Hofer distance. This one, so I feel that one has to kind of define more kind of more coarse topology, kind of contain both of them. you have this another topology, right? Coming from this change of this S1. It kind of gives this rigid analytic space of the moduli of Lagrangian sum-manifold, and then kind of, the rigid analytic space, you have some core part, and in each core part, you have some kind of very more complicated kind of very nasty part. I mean, very small part is infinitely many branched trees or something like that. And this infinitely many branched tree kind of things is I believe related to this Hopper topology. But this one, you have this core is S1. So this topology on this S1 part is not captured by this Hopper distance. So by this reason, that the definition I gave today probably is not strong enough to study Calabi-Yau case.
Okay, yeah. All right. Okay, so I just do not understand whether we have already discussion or
Yeah, probably it is, yes.
All right. If this is a discussion, other questions.
So I was wondering if you have any computation of in the algebraic geometric case. For instance, say you have a formal scheme, and then you like over Novikov ring, and then you blow up, for instance, in the special fiber. Like, do you have a computation of the Gromov-Hausdorff distances of the categories associated to blow up and the original formal scheme?
Yeah, I think so. You have a formal scheme. That I think is very kind of definition is easy. So suppose you have this formal scheme. It's a kind of scheme over spec lambda 0, and you have this two. Suppose that you have two sheaves. Or maybe chain complex for two sheaves. And we assume that after going to this generic point, they are homotopy equivalent. You have a phi. Then we can say that so we can just say that this distance smaller than epsilon. So that's something like T epsilon phi is contained in defined over lambda 0. So it's defined over lambda 0, and the psi, T epsilon psi is also defined over lambda 0. So you have this homotopy equivalence, but you generate at the denominator. And you see that how the denominator should be. That's these definitions.
And for instance, do you have examples of such formal schemes where the distance is actually positive?
Sure, you can just very easy. So you can just take lambda 0 itself. And take this lambda 0 divided by T over A lambda 0 and 0. This distance is A.
Okay, thanks. But this is not flat over lambda 0. Okay. Is there like just for instance, like if you blow up in this special fiber, does it give something different or in distance wise?
But could you repeat your question?
Can you, for instance, take a formal scheme and make a blow up in the special fiber?
Mm-hmm.
Does it give something of positive distance to the original one?
But what do you mean by this? Grow up gives an object?
Sure, blow up. I mean, like.
Blow up gives a different x, but this is a kind of distance from the category of coherent sheaves.
Yes. Yes, it gives a different x, but if it gives a different category of coherent sheaves. So I was wondering if the distances of the blow up category and the
blow up category, right? Yeah, my feeling is that this lies more on a kind of rigid word than kind of the formal word. It means that I think the rigid word blow up at the origin does not change the rigid space, right? Somehow. So blow up probably gives more objects somehow. And I think the correct way to think is just you consider this all blow ups and take inductive limit. That I think is what rigid geometry is doing.
Yeah, that's what it is doing. It consider all models for the unique analytic space which is obtained by this localization from, say, derived.
Yeah. And then this Hofer distance gives this metric on this all the object derived category coherent shape on this rigid space, and that is somehow, you know. And if you take some kind of this Gromov-Hausdorff distance is, if you consider some subset of this all coherent shapes, then you get some subcategory. So you take this all derived category of coherent sheaf of this rigid space. You take this two set A and B, and you can consider this infinity category so that the object set is this A or B. Then you take this usual Hofer distance, the usual Hausdorff distance with respect to this kind of Hofer distance. Then this is something like equal to this Gromov-Hausdorff distance between this category. So you know this guy is somehow enough dense. It's something related to this generator things. So that's okay. Jan, you mute.
Yeah, I am mute. Sorry, so I was asking whether whether you are satisfied with the answer, or maybe you want to ask more. Otherwise, we will go on.
Oh, that's fine. Yes, yeah.
Okay. Yeah, actually, I have one comment which I'm not sure whether it's relevant, but it's some analogy. It's not in the framework of the usual Floer theory, but this holomorphic Floer theory, which we are developing with Maxim for years. Actually, it started, I believe, on the way to Simon Center like 7 years ago. Yeah, you see, if your symplectic manifold here is a holomorphic, is complex, then kind of the usual Floer theory doesn't tell you much, because kind of the Morse differential, the Morse indices of different points are the same. So it's a different theory. You should consider everything in families. But there are two types of categories, or rather family of categories, which you can associate. And one which is interesting, it's a deformation quantization. It's a category of, you can quantize your complex symplectic manifold, like cotangent bundle. You associate to it a sheaf of differential operators. Yeah. And similar thing you can do for any complex symplectic manifold. And so you get something which is defined over a formal power series in one variable, like Planck constant. It's an analog, if you like, of the Novikov ring. And what people normally do when study the modules, objects in this category, they invert this Planck constant, which means that this is analogous to going from Novikov ring to Novikov field. Of course, they lose something, but anyway, in this framework, we formulated with Maxim a certain generalized Riemann-Hilbert correspondence. So on one side, there is a category of certain like holonomic modules, or this deformation quantization with a Planck constant inverted, which means it's analog to, if you'd like, of the category of coherence sheaves, but over Novikov field. On the other side, we have a family of Fukaya categories, which is obtained like this. We take the holomorphic symplectic form, we rescale it, we divide by the Planck constant and take the real part. So, all right. So then you see again, the parameter is inverted. And so the theorem or conjecture, but it's can be checked in many cases, these two categories over, let's call them Novikov fields, they are equivalent. But after your talk, today's talk, it looks interesting to consider, I think, in that framework, the categories where this Planck constant is not inverted, because we didn't know what should be on the Fukaya side. And now it looks like you can say something. So there might be kind of an upgrade of this theory, which, yeah, so it's interesting. Okay, but it's a comment, it's not a question.
Yeah.
Now more questions, maybe more comments.
I have a question, not a comment. So, so of course, this right in your book, right? You have all these theorems about how you can, if you have a displaceable Lagrangian, right? If you consider Floer homology with this Novikov ring, right? Then you look at distortion pieces, right? And that you bound like Hofer energy and stuff to displace it, this sort of thing, right? So my question is kind of, you can speculate as much as you want, is what sort of Hamiltonian dynamic things do you think this category recovers that the other one doesn't? Is there any specific thing you have in mind, or
So yeah, I mean, expectation is that it should know almost everything, but it's very complicated things. And I can mention one dream problem.
Okay.
One dream problem is the following thing. Suppose you consider modular space of Lagrangian submanifold, and you take its completion by Hofer metric. And this is something like a modular space of object of this AVT category by lambda 0. And if you go to this mirror, it's something like a kind of an object of this some kind of coherent sheaf over rigid spaces. And that kind of thing is, in a sense, my feeling is something similar to Berkovich spectra. You know, it's a kind of all the modular spaces of this on this rigid spaces. And what's very looks interesting is that Berkovich spectra is some kind of an infinite dimensional analog of Titz building. So, I mean, Titz building is some particular case of this Berkovich spectra, as far as I understand, in the case of local symmetric spaces.
Yeah, Drinfeld space.
Yeah, and then if you go to this thing, it gets much bigger. It's infinite dimensions, but it's kind of similar kind of structures. And something I will be very happy if I can do anything on this direction is I want to try to prove some fixed point theorem on this Berkovich spectra type things. Why it is interesting? Suppose you have a Hamiltonian diffeomorphism. It gives some automorphism on the space of modular space of Lagrangian submanifold. And I want to prove fixed point, existence of fixed point. It means that I want to try to prove there's some invariant Lagrangians of Hamiltonian dynamics. That's one of the major problems. And what's interesting is that this is not a Lagrangian, but it's kind of infinite of Lagrangians. So the dream is in CAM theory, it is known as KM. It is known that you have any kind of near integrable systems. Many invariant tori just destroyed. But we may expect that even in this infinite, even for this chaotic things, it may still exist some in a completion of this moduli of Lagrangian tori, it may have a fixed point. And you know, proving fixed point theorem on a Titz building is very classical things. It's most of himself who first to prove it for the higher rank. So I just dream is that I can try to prove this any fixed point theorem on the modular space of Lagrangian submanifold to give some existence of some invariant Lagrangians. But that's very difficult, as you can see.
More questions?
Yes, I do have a question. So here, and for the Novikov ring you used here, the real number is nothing special. You could take any complete totally ordered field. that should work. Am I right?
Yeah,
Ma-
yeah,
maybe
yeah, yeah.
maybe
I
can
believe,
you-
but the example for Lagrangian Floer theory is in the case of real number. So that's why I just, yeah. And in an abstract case, yeah, of course you can do anything.
Okay.
This was your question. Okay.
Mhm.
More questions? And by the way, Kenji, I have noticed that you had a paper, related paper, this year, submitted this year in the archive. To the
Yes,
archive.
yeah, yes.
Okay.
That proved this theorem about this triangle inequalities or completeness or something like that.
Okay, so people who are interested, they can learn more in that paper. Okay, more questions?
And so in this approach, you still only consider unobstructed Lagrangians, right? You never try to include obstructed.
No. So you know that's one of the conjectures I mentioned, that you consider all Clifford type tori. You have a complex symplectic manifold. If you take Darboux chart and you take this Clifford tori, and you consider all of them, that's finite dimensional family. And the conjecture is that is generator. And even if you try to formulate these conjectures, Clifford tori in this case is actually obstructed.
Yeah.
So you have some obstructed infinity category. And I still believe the module category of right module over this obstructed infinity category is well defined. And it can contain an unobstructed object. So if you try to prove this kind of conjectures, that I think is interesting to have a kind of generator like this local things.
Yeah.
But then the first thing I want to do is just to formulate the notion of this Yoneda embedding, or kind of infinity category over some curved infinity category, so that all objects is obstructed. And then try
I
to
kind of did that, right?
yeah.
When I was writing my thesis, right, I did this tensor product. I kind of did the embedding for curved things.
Yeah.
Of course, I just for one algebra, right? So one single object. But I think it works in.
Yeah, I think it works. Yes.
Yeah.
And then we need to cook up this open closed map from this, kind of only local torus is an object, and try to prove that this open closed map fit unit. And the idea should be that you have kind of enough many small tori, then you have enough disk so that it hits every point. So that in principle, that kind of argument should work. So it should imply that this local tori, Clifford tori, knows everything in Lagrangian Floer theory. It seems that this Tamarkin's work is somehow related to this kind of things.
I also wanted to say. More questions? So, last chance to ask Kenji something. Well, if not, well, thank you very much for very interesting talk, very inspiring.
Okay, so thank you, coming.
And this is it. And this is, thank you. This is the last term seminar, as I said, and so we'll have a break until the next semester. Okay.
Next year.
Bye-bye.
Next year, next